In this video, we'll get to talk about the fact that there is a direct connection for rigid body rotating objects between these angular variables that we've been defining and the linear variables. Now, we shouldn't be surprised at that. We didn't change physics or anything of rotating objects. We could have counted and used x, y, and the Cartesian coordinate system to do all this work. It would have not been practical, but it was nothing wrong with the physics. All we did was change our coordinate system in the way that we labeled vectors. So there should be a one-to-one relationship between these new quantities, angular position, angular velocity, angular acceleration, displacement, and all those variables that we had before. Regular position, acceleration, velocity, displacement. The fact is there is. By simply changing and swapping out symbols in our formulas, we can generate a whole new set of equations anytime we want, and we can take advantage of all that work that we did back in chapters 2 and 3 and 4 and 5 and 6 and 7 to do a whole new set of problems without having to relearn large amounts of material. This is why it's important to study concepts and not memorize formulas. If you memorize formulas and you've got 100 or 200 formulas, then suddenly you have to learn 200 new formulas. If you understand concepts, you get the whole new 200 formulas with nothing being required to be learned practically. So you're suddenly able to learn twice as much material in a lot less time. This will stay true in lots of other courses as you go along. So you have to learn how to learn, or you can't keep up. The trick of this is what I like to call the big board. It's a connection between linear variables in one land and rotational variables. You can think of it as like learning two languages, Spanish and English, for instance. There is some property or something you want to describe, like lunch, or a table, or a house. And there may be two totally different words, one of them in English and one of them in Spanish. When you're in Spain, you speak the Spanish. When you're in England, you speak the English. Same sort of thing here. When you're in linear land, you use linear variables and linear concepts. When you're in the angular land, you use the angular concepts. Properties that we know that we can develop analogs for include position, defining something and where it's located. The linear variable is x. The rotational variable is theta. Velocity. We use the symbol v when we're in linear land. When in rotational land, we use omega. Acceleration, we use the symbol a. When rotation land, they use the symbol alpha. There's a thing called inertia, desire to continue in your state of motion. That was in a straight line at constant speed, and we use the symbol m for mass. In rotation land, there'll be something too called rotational inertia. But since we understood the concept better, we actually used the symbol I for inertia. The cause of acceleration is force in linear land. The cause of angular acceleration is called torque, and we'll learn how to compute it later on. There is this desire of an object to continue called its momentum. We use the symbol P in chapter 7. There'll be angular momentum. We used an L for that. And I'm not quite really sure why we used angular L. The fact is the engineers will use a different thing, and they call it something different. They call it a moment. You have these things where these torques and these L's, they call things different, but that's okay. Energy, there's an E. Well, energy is not dependent upon a particular spatial coordinate system. It's a scalar, so it didn't get changed. Kinetic energy doesn't get changed. Potential energy doesn't get changed. Time is a scalar. It doesn't get changed. If you learn this table and put these symbols to memory, you can show absolutely amazing ability to solve problems, because you can convert any problem from chapter 2 and chapter 4 and so forth into a new problem in this chapter. Let me show you how we can do that. Let's start with rotational kinematic equations. In linear land, we had constant acceleration. That's in linear land. And we had these equations. X was the initial position, initial velocity times time, plus 1/2 the acceleration times time squared. We also knew the final velocity was equal to the initial velocity plus the acceleration times time. And the final speed squared was the initial speed squared plus 2 times the acceleration times the change in the position. Now we want the similar rotation. You have to have constant angular acceleration for these equations to be true. And the equation is you replace x with its equivalent, which is theta. And the angular position is equal to the initial angular position plus the initial angular velocity times time plus 1/2 the angular acceleration times time squared. The final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. The final angular speed squared is equal to the initial angular speed squared plus 2 times the angular acceleration times the angular displacement. We simply replace the variable in linear land with its equivalent off the big board, and we get the whole new set of equations to work problems. All of the graph problems that we did before, like the area under a velocity time graph gives you displacement. The area under an angular velocity time graph gives you angular displacement. Everything that we did before in chapters 2, 3, 4, 5, we now can do angular type equivalent. You have Newton's second law. Sum of the external forces is equal to mass, that's inertia, times acceleration. That becomes the sum of the external torques is equal to the moment of inertia times the angular acceleration. We had this thing about the sum of the external forces equal the change in linear momentum over the change in time. Well, the sum of the external torques will be equal to the change in the angular momentum over the change in time. And we can talk about collisions and isolated systems for rotation. We had a formula for calculating kinetic energy if the object has constant rotational inertia. Well, we said that kinetic energy was 1/2 mv squared. K rotational energy is equal to 1/2 rotational inertia, that's the moment of inertia, times the angular speed squared. We simply change the variables from our formula in the previous chapter and we get a whole new one. This one calculates the energy an object has due to motion, for instance if it was spinning like a circular saw. This one calculates the energy an object has if it's moving along, for instance like a car. All of our past work is available to us. Gorgeous problems. And I could do a lot more different formulas. Almost any formula that you could think of. Remember, P was mv. Well, then angular momentum should equal I omega. And in fact, it does. So if you've got a formula in linear land, I now have a formula in angular land for it. And I don't have to go do double the work memorizing it. I just needed to really pay attention throughout this time that we've been doing it and spent the time learning all of these linear formulas, and now I get paid a bonus because I know all the angular formulas. Kind of a way of showing how all this puts together and talking about all of these rotational things and how you can use these to solve these various stuff. I want to take an example. You have a wheel. It's rotating at constant angular speed for 4 seconds. Okay. Goes along here for 4 seconds at a constant omega. So it stays flat. It then decelerates. So here's 4 seconds. Decelerates till it comes to a stop 6 seconds later. That's 10 seconds. The wheel rotates to a total angle of 300 rads. That's delta theta. 300 rads. That's the area under this curve. So I know that 4 omega, that's the area of this rectangle, plus this, which is 6 omega over 2, that's the area under that triangle, 1/2 base times height, is equal to 300 rads. They want to know what omega is. I can find that. You won't find a formula like this in the book. You have to find it by finding the area under the curve. So 6 over 2, that's 3. 3 plus 4 is 7 omega, is 300 rad. Omega, of course this is in seconds. Probably should have put the units there. So omega is 300 over 7 rad per sec. Take my calculator. 300 divided by 7, I get 42.9 radians per sec. That's the answer to the problem. Knowing the fact that the area under a velocity time graph is displacement tells me that the area under an angular velocity time graph is angular displacement. Go back and look at the problems that we did early in the semester and see the connection between VT, where this was delta x, the displacement, and this, where this is angular displacement. Those graphs and the time you spent there is now going to get you some extra points because you can now do a whole bunch of new problems in angular land. Okay, talk to you on another video.